Now, let us look into another problem as per which the system function of a LTI system is given as h of z is equal to 1 minus 2z inverse divided by 1 minus az inverse multiplied by 1 minus bz inverse, where 0 less than a less than b. There are four options given corresponding to this system. We have to pick the correct option. As per option A, if A equal to 3, it's possible that the system is both causal and stable. As per option B, if B is equal to half, it's possible that the system is non-causal and stable. As per option C, if A equal to 1 by 3 and B is equal to 3, then it is possible that the system is non-causal, non-anti-causal, and stable. As per option D, if A equal to 1 by 4, then mod z less than 1 by 4 is possible ROC of the system. Sorry, mod z less than 1 by 3 is possible ROC of the system. We have to pick the correct option out of these four. So, as per option A, we see that the possible ROCs are mod z less than 3 and 3 less than mod z less than b. Sorry, as per option A, it is given that A is equal to 3, which is less than B. So in this case, the system is stable for the ROC mod Z less than 3, but in this case, the system is anti-causal. So the option A is not correct one. Now, as per option B, it is given that A is less than B is equal to half. In this case, the system is stable for the ROC mod z greater than half. So, in this case, the system is causal. So, the option B is also not the correct one. In case of option C, it's given that A is equal to 1 by 3 and B is equal to 3. So, the possible ROCs are mod z less than 1 by 3, 1 by 3 less than mod z less than 3, and mod z greater than 3. In the first case, the system is anti-causal, non-causal, and unstable. In the second case, the system is non-causal, non-anti-causal, and stable. In case of option C, the system is causal and unstable. From this, we see that if A is equal to 1 by 3 and B is equal to 3, it is possible that the system is non-causal, non-anti-causal, and stable. Now, so C could be a correct option. However, if we consider the option D, in which it is given that A is equal to 1 by 4, which is less than B, here we know that mod z less than 1 by 4 is possible ROC of the system. But so from this, we can say that mod z. So from this, we can't comment if mod z less than 1 by 3 is so okay. Mod z less than 1 by 4 is the possible ROC of the system. So mod z less than 1 by 3 is not surely a possible ROC, as the ROC shouldn't contain the pole which is 1 by 4 in this case. So from this, we see that in case of option C, if A is 1 by 3 and B is 3, we see that the system is non-causal, non-anti-causal, and stable. Sorry, it is possible that the system is non-causal and non-anti-causal and stable. So option C is the correct one. Now let us look into another problem as per which it is given that There is a system which is described by the LCCDE. Please note that the system is LTI. The LCCDE that represents the LTI system is y of n minus 3 by 2 y of n minus 1 plus y of n minus 2 is equal to x of n minus 3. It's given that the system has a impulse response of h of n. It is also given that the system is non-causal and unstable. In this case, we need to find the ROC of the system function h of z. So here we see that there is a LTI system with LCCDE as shown, and the impulse response of the LTI system is h of n. It's given that the system is non-causal and unstable. We need to find the ROC of h of z. From the given LCCDE, by taking z transform on both sides, we can obtain the system function as h of z is equal to y of z by x of z is equal to z power minus 3 divided by 1 minus 3 by 2 z inverse plus z power minus 2. This can further be simplified as z power minus 3 divided by 1 minus half z inverse multiplied by 1 minus 2 z inverse. From this, we see that the possible ROCs are mod z less than half, 1 by 2 less than mod z less than 2, and mod z greater than 2. We see that in case of 1 is the system is anti-causal, non-causal, and unstable. In case of 2, we see option 2, we see that the system is non-causal and stable. In case of 3, we see that the system is causal and unstable. From this, we see that as the system is non-causal and unstable, mod z less than half is the ROC of the given LTI system. Now, let us look into another problem as per which there is a LTI system of impulse response h of n, and the z transform of h of n is given as h of z. It's given that the LTI system is anti-causal and stable. Then we have to find the possible ROC of h of z out of the options given. Here the option A corresponds to the ROC mod z greater than 2. Option B corresponds to mod z greater than half. Option C corresponds to mod z less than 3. Option D corresponds to mod z less than 1 by 3. If we consider the option A, the system would be causal and unstable. So this is not the correct option. If we consider the option B, the system would be causal and stable. So this is also not the correct option. If we consider the system in option C, the system would be anti-causal, hence non-causal and stable. So this is the correct option. If we consider option D, the system would be anti-causal, non-causal and unstable. So this is also not the correct option. So the ROC of the system function h of z, which satisfies the conditions of anti-causality and stability, is mod z less than 3. So please note that this is just a possibility. So the option C is the correct option. It's given that there is a LTI system of system which has the system function as h of z is equal to 1 by 1 minus 2z inverse, 1 minus 3z inverse. It's given that the system is causal and stable. From this, we need to find the impulse response of the LTI system. By splitting the given h of z into partial fractions, we get that h of z is equal to a by 1 minus 2z inverse plus b by 1 minus 3z inverse. This is equal to a into 1 minus 3z inverse plus b into 1 minus 2z inverse divided by 1 minus 2z inverse multiplied by 1 minus 3z inverse. Upon equating the numerator 1 with the numerator of the h of z that we got, we see that a plus b is equal to 1, which corresponds to constant term, and minus 3a minus 2b is equal to 0. That implies a is equal to minus 2b by 3. Upon substitution, we see that b is equal to 3. From this, we can say that a is equal to minus 2. So the system function h of z can be written as minus 2 by 1 minus 2z inverse plus 3 by 1 minus 3z inverse. Also, we can say that the ROCs possible for the given h of z are mod z less than 2, 2 less than mod z less than 3, and mod z greater than 3. In the first case, the system is anti-causal. Sorry, please note that it's given that the system is causal and unstable. So for mod z less than 2, the system is anti-causal and stable. For option B, the system is non-causal and unstable. In case of third ROC, the system is causal and unstable. So from this we see that mod z greater than 3 is the ROC of the overall system. So the individual ROCs can be written as mod z greater than 2 and mod z greater than 3. From this we can write that the impulse response of the LTI system is equal to minus 2 multiplied by 2 power n u of n plus 3 multiplied by 3 power n u of n. So this is the impulse response of the given LTI system. In the above example, if the system is causal and stable, find h of n. From the obtained ROCs, we see that causality and stability are not possible together. From this, we can say that the impulse response h of n, which satisfies causality and stability, does not exist. Now, let us consider another problem, as per which it is given that there is a discrete time LTI system which is given an input of x of n is equal to delta of n minus delta of n minus 2, and the impulse response of the LTI system is h of n is equal to delta of n minus 1. We need to find the output of the LTI system for above input. The z transform of the input x of z can be written as 1 minus z power minus 2, and the z transform of the impulse response, that is the system function, can be written as h of z is equal to z inverse. From this, we can write that the z transform of the output y of z is equal to h of z multiplied by x of z. This is equal to z power minus 1 minus z power minus 3. From the definition of the Laplace transform, we can write that the output of the LTI system is 0, 1, 0, minus 1, where the value of 0 corresponds to the instant n is equal to 0. So from this, we can say that for the given input to the LTI system of impulse response delta of n minus 1, the output is 0, 1, 0, minus 1. Now let us look into another problem, as per which the impulse response of a causal LTI system is given as h of n, and z transform of h of n is equal to e power 1 by z. From this, we need to find h of n. Please note that it is given that the system is causal. So using the power series expansion, we can write that h of z is equal to e power 1 by z, which is equal to 1 plus z inverse by factorial 1 plus z power minus 2 by factorial 2 plus z power minus 3 by factorial 3 plus and so on. This can be written as sigma n equal to 0 to infinity 1 by factorial n into z power minus n. From this, we can write that the impulse response of the LTI system is 1 by factorial n into u of n. Now, let us consider another problem as per which it is given that the impulse response of a LTI system is h of n. From this, the system function of the LTI system is h of z is equal to 1 minus z inverse multiplied by 1 minus z power minus 2 with the ROC as mod z greater than 1. We need to find h of n from this. The system function h of z can be simplified as shown, that is h of z is equal to 1 minus z inverse whole square multiplied by 1 plus z inverse. Please note that the ROC here is mod z greater than 1. Upon splitting this into partial fractions, we get that h of z is equal to 1 by 4 multiplied by 1 minus z inverse plus 1 by 2 multiplied by 1 minus z inverse whole square plus 1 by 4 multiplied by 1 plus z inverse. Here the ROC is mod z greater than 1. Therefore, the impulse response of the LTI system can be written as h of n is equal to 1 by 4 into u of n, which is inverse z transform of 1 by 1 minus z inverse plus 1 by 2 multiplied by minus 1 whole power n u of n, which is inverse z transform of 1 by 1 plus z inverse plus 1 by 2 multiplied by n plus 1 u of n. This can be obtained by using the identity z transform of n into x of n is equal to minus z into d by dz of x of z. With this, and also note that 1 by n plus 1 into u of n is inverse z transform of 1 by 1 minus z inverse whole square. So from this, the overall impulse response becomes h of n is equal to 1 by 4 plus 1 by 2 minus 1 whole power n plus 1 by, sorry, this is 1 by 4 minus 1 whole power n plus 1 by 2 multiplied by n plus 1 as a whole multiplied by u of n. This is the impulse response of the overall LTI system. Now let us consider another problem as per which it is given that there is a LTI system of impulse response h of n is equal to 1 comma 0 comma minus 1. It is cascaded with another LTI system. Sorry, please note that here the value 0 corresponds to the instant n is equal to 0. It is cascaded with another LTI system of impulse response h of n is equal to 1 comma minus 2 comma 1, where the value of 1 corresponds to the instant n is equal to 0. The cascaded system is given an input of x of n is equal to 1 comma 2, where the value of 2 corresponds to the instant n is equal to 0. We need to find the output y of n of the cascaded system. From above, we can see that the system function h1 of z is equal to z minus z inverse, and the system function h2 of z is equal to 1 minus 2z inverse plus z power minus 2. From this, the overall system function can be written as h of z is equal to h1 of z multiplied by h2 of z, which upon simplification becomes z minus 2 plus 2z power minus 2 minus z power minus 3. But it is given that the cascaded system is given an input of x of n is equal to 1 comma 2. Sorry, here the value of 1 corresponds to the instant n is equal to 0. So x of z is equal to 1 plus 2z inverse. Therefore, the z transform of the output y of n is given as y of z is equal to h of z multiplied by x of z, which upon simplification becomes z minus 2 plus 2z power minus 2 minus z power minus 3 plus 2 minus 4z inverse plus 4z power minus 3 minus 2z power minus 4. So upon simplification, the output y of n can be written as 1 comma 0 comma minus 4 comma 2 comma 3 comma minus 2. Here the value of 0 corresponds to the instant n is equal to 0. So as per the problem, there are two LTI systems of impulse responses h1 of n and h2 of n. So based on these impulse responses, we found the overall system function of the cascaded system. It's given that the system is given an input of x of n. From this, we found y of z as h of z multiplied by x of z. So the output of the LTI system can be obtained as 1 comma 0 comma minus 4 comma 2 comma 3 comma 2, with the value of 0 corresponding to the instant n is equal to 0.